This is the second week of the course. My name is Amit Shaw. As it was mentioned in the introductory class, I will be sharing some of the lectures along with Professor Vishwanath Banerjee. So, this week we will be discussing concept of stress and strain. You see, some of you maybe studying civil engineering, some of you aerospace engineering, some of you mechanical engineering. So, you all are studying different engineering disciplines. As you go higher, you will see the gaps between different engineering disciplines reduce, and anything that comes out from industry, they are essentially the outcome of handshaking of different engineering disciplines. It is not just for one engineering discipline, it is the concept of different engineering disciplines put together, and then we get a product from an industry. Now, therefore, there are few places where all these different engineering disciplines, they share a common thread, and the subject of this course, as it was mentioned in the first lecture, subject of this course is one such thread. You see, there is a saying that nature is the best engineer, right? And we all try to understand nature, we all try to mimic nature. Nature is governed by certain rules, and we try to understand those rules. But just understanding those rules is not enough. We need to translate that understanding into a form which can be used to develop a product, different kinds of product, eventually for the development of mankind. Now, if I have to give you some examples of some of the products, these are some products. You see, these are some representative product. While selecting them, I try to keep in mind that different scales can be covered, different application domain can be covered. So, this product could be as large as say bridge building, or as small as say nanorobot. This product could be different kinds of vehicles, then motherboard or computer, then the jackets, then the switchboard that you can see in your house, the optical fibers, CD, the pacemaker that we put in human body, and even the SIM card. So, all these products that you can see now on your screen, on the screen of your monitor, you can all relate to those products. Okay. In fact, there are many such things. Now, you see, they are all designed to serve certain purposes, and their purposes are different. Okay. And in order to design these different products, we need different skills. But one of the major difference in all these products are, if you look at them, they all are made of different materials. For instance, the material that I use for say bridge, the same material cannot be used for nanorobot, or the materials used for bridge cannot be used for switchboard, or the material used for switchboard cannot be used for bulletproof jackets, or the same way the material used for bulletproof jackets cannot be used for the optical fiber. So, every product has their own purpose to serve, and depending on that purpose, these products are made of different materials. Okay. Now, at this thing we all know that. Now, when we design anything, one of the very crucial step in the design is selection of this material, and that material selection has to be based on the purpose of the final design, and the environment that is the final design the product is subjected to. In some cases the environment is extreme, some cases the environment is not extreme. For instance, if an aeroplane is flying, then the outside temperature could be -40 to -50 degrees Celsius, whereas if you take a bridge, the outside temperature is not that extreme. It is just one example. So, different products are subject to different kinds of environment. So, we select a material which can sustain that environment, which can sustain that threat that may come onto the product. Therefore, understanding of material the behavior of material when it is subjected to certain kind of threat is a very important step. And so, what is, we have a material and which is subjected to some kind of threat, and then what is the response of that material, and that threat could be different. That depends, that is very subjective, that depends on the which is the purpose, for what purpose we are using this material, whether and under what circumstances, under what environment the product will be exposed to. So, depending on that, the threat has to be considered. Okay. So, now, but overall the important thing is the response of the understanding of the response of the material when it is subjected to certain kind of threat, and that is the crucial point, that understanding is the crucial point in any design. Okay. Now, this course is essentially a first step towards that understanding. Now, this response, this entire thing, there are three important parts in that understanding. When we talk about the understanding of material behavior, it has three important parts. One is stress. Let us not bother about what is stress, what is strain now. We'll shortly come to that point. One is stress, one is strain, and then how the stress and strain related to each other. Stress is a function of strain, which is called material constitution. Okay. So, this is three important part in material characterization. Okay. Material characterization is the understanding how the material behaves when it is subjected to different loads or different environment. Now, what we will be doing in this week is we will try to understand what is stress and strain, how they are defined, how they are measured, what are the physicality associated with stress and strain, and then next 2 weeks, week 3 and week 4, we will see what is the relation between stress and strain, and that relation is not same for all material. Depending on the material, that relation may change. So, in the next week we will consider different kinds of material, we will idealize those material, and then see what would be the relation between stress and strain for different idealization. So, let us start with stress today. Now, you see, again, stress is the term. It is not particularly associated with theory of elasticity. It is a very general term, and we all use this term very often in a different perspective. For instance, we often say that don't take any stress, otherwise your blood pressure will increase. You see, so stress is what, suppose you have a workload in office, you have exam around the corner, you are moving from one place to other, don't know the place, don't know the people, then you are stressed. So, stress is essentially, it is the response of human body. We are trying to define stress from a different context. We'll see what is their interpretation in the context of material characterization, in the context of elasticity, but let us understand the word stress, what is the general use of stress, and believe me, the general use of stress has the same meaning when we come to the interpretation of that in the context of elasticity. It is exactly the similar thing. Now, stress is what? It is the body's way of responding to any kind of threat, and that threat could be anything. And we all have experienced stress in some point of time. Now, let us entirely call all these different kinds of different causes, different reason for stress. We can put together and let us call this threat. Okay. So, when we say threat, it is very subjective, it depends on the what context we are talking. Now, you see, stress is something that we cannot visualize. It is an experience, right? If I am stressed, I can experience that, but someone looking at me cannot experience that stress, that cannot visualize that stress. So, it is something which is experienced, but it is not perceived by someone else. But there is, so stress is a response of human body, but it cannot be visualized by someone else. It is an experience. But there is another response of the same human body which can be visualized. For instance, if you are constantly, if someone is under constant threat, constant load and constant stress, then the health may get deteriorated, the blood pressure may increase, sugar level may increase, the weight, the person may experience weight problems. So these are some consequences of that threat acting on the human body, but that response can be measured, response can be visualized, isn't it? So these are the some response. This is just an example. These are the some responses which are visualized, which can be perceived, unlike stress. So let us call all together this entire thing is strain. Okay. So when a human body is subjected to some kind of threat, then as a response we have stress, and then another response is strain. Right? So now, and we all know this. Now what we do is not only just the human body. If a material is subjected to some kind of threat, then the material is also experience stress. But again, as I said, it is just an example. The threat is different for material. But again, if the material is subjected to a different environment, then the material also experiences stress. But again, in the same way, that stress is something that material experience, it cannot be visualized. But there is another response which is strain, which can be visualized. For instance, take one object, say it's a paper cup. Okay. Now, if I apply some load like this, so this paper cup experiences stress, but we cannot see that. But what we see is as a consequence of this load, as a response to that load, this paper cup undergoes severe deformation, and this deformation is related to strain. Okay. Now, so what we have here is again we come to the mechanics of material, which is essentially the understanding the response of material. Now, this response has two parts. One is stress, one is strain, right? And then we will now understand what is stress and what is strain and how they are defined, how they are measured. Okay. Now, come to the once we have understood that the stress and strain are two responses to different kinds of responses of a material. Now, let us define what is stress. Now, before coming to the definition of stress, let us go back to your school days. This is not the first time, even in the context of mechanics, this is not the first time that you are encountering the term stress. In your school days also you use the term stress. Remember, suppose if I have a bar, longitudinal bar, and then which is subjected to some kind of load P, okay, like this P. Suppose this longitudinal bar as a cross section, this is the cross section of the bar. This cross section is suppose A. So, recall we define stress as stress is equal to P by A, or more fine definition is stress is equal to limit A tends to 0 P by A. Okay. Force by area, that is how we define stress. Okay. Now, now whether it is the tensile, the load is tension or load is compression, depending on that the stress can be coined as tensile stress or compressive stress. Okay. Now, this, when you apply this load, this will cause change in length of this rod. Now, suppose the initial length of the rod is L, and then after deformation, if the rod becomes like this, the length may increase, length may decrease depending on whether whether it is compressive load or tensile load, it is delta L. Then recall, we define strain as delta L by L, right. So, this is the definition we used in our school days, and we all are familiar with this definition. Now, there is what we have to do now is we have to move beyond this definition. There is nothing wrong in this definition. This definition is absolutely fine definition, and we will be using this similar definition. But now, when we say the stress is equal to force by area, then the question naturally comes, which area and which force? Or the strain is equal to change in length by original length, then naturally the question comes is which length change in which direction divided by length in which direction. So, depending on that, we have to move beyond this definition. For instance, let us see, let us take an example. Suppose we have an object, suppose this angle is theta, okay. Now, suppose the load of this is acting downward like this, and this is W, okay. Now, so what exactly we are doing is we will be discussing the stress and strain in detail. We are just trying to set the platform today, being this since is the first lecture on stress and strain, and then from the next lecture we will see the different stresses, how they are represented and how they are measured and everything. So, suppose the load is acting downward. So, naturally we have two components of this load, one is this tangential direction and one is normal direction, right. So, say it is W1 and this is W2, okay. Now, suppose this area is this area is suppose A, area is A. Now, you see on this area we have to, just now we discussed the force, stress is equal to force by area. Now, we have on the same area we have two forces, one force is normal to this area and another force is tangential to this area. So, if I stick to that definition that stress is equal to force by area, then we have two forces here, two stresses here, then stress 1 would be, stress 1 is equal to W1 by A, and then stress 2 is equal to W2 by A. One thing please note, I am not yet writing any symbol for any notation for stress. Stress 1 and stress 1 we are writing, we will formally introduce what are the notations and how it is to be written in subsequent classes. Now, we have two stresses. So, one stress is this is one stress, this is one stress which is acting, which is normal to this, and another stress is which is acting to this, okay. Now, this stress is called normal stress, and this stress is called shear stress, okay. So, stress is now is just not one quantity, it has, in this context at least we can see it has two component, one is acting normal to this plane and one is acting shear to this plane. Now, you see definition is again still same, the force per unit area, but now since we have two forces on the same area, we have two stresses. Similarly, we will not discuss right now. When we come to the nonlinear elasticity, then we will see that we may have different definition of area. Therefore, depending on the which area we are talking about, we can have again different measure of stresses. Okay, let us do it in 3 dimension. Suppose in the same problem, suppose this is first, let us fix the suppose on this plane, suppose this is the, let us fix the coordinate axis first. This is and this is the coordinate axis. Say this is x, y and z. Now, on this coordinate axis, suppose we have a load which is like this, so P. Now, this pli makes an angle with all these axis x, y and z, and if it is, then P will be having 3 components. What are these 3 components? One component will be normal to this, suppose this is P1, another component will be tangential to this in this direction, which is say P2, and another component will be tangential to this, which is in this direction, which is say P3. Then we have 3 stresses on the same plane, then stress 1 will be P1 by A, and similarly stress 2 will be P2 by A, and stress 3 will be P3 by A. P3 by A. So, we have 3 stresses, stress still force per unit area, but now we have 3 component of stresses. 2 stresses are, this is normal stress because it is acting normal to the surface, and this is shear stress, this is, and this is shear stress, right. Now, once we have understood that we have to move beyond that definition, because now we may not be dealing with just one force or one area, we can have different kinds of forces acting on the same area, or for the time being, let us consider the same area, different kinds of forces acting on the same area, and therefore, we can have different measure of stresses, different components of stresses. Instead of measure, we say different component of stresses, and these are the component of stresses. Normal stress is one component, shear stress is another component. Now the next is, so therefore, now next is, when we say what is the stress in a body. Okay. For instance, suppose we have, now we want to introduce a very important term called infinitesimal area and volume. Now, suppose take any object like this, which is subjected to some external threat. In this case, the threat is some external loading. Okay. Now, because of this threat, this object, this material will experience some stress. Okay. Now, when we say that, if I ask what is the stress in this material, or rather what is the stress in this body or in this object, this question is vague. This question is not this question is not properly posed, because stress is a point wise description. Means, if we take several points in the body, if we take several points like this in the body in the same object, then the stress at different points are not same, they may be different. Okay. So, if they are different, then we cannot ask, we cannot say what is the stress in the body, rather we have to ask what is the stress at a given point in the body. So, stress is a point wise description. When we say what is the stress, implicitly it means what is the stress at a given point. Okay. Now, just now we discussed that stress is equal to force per unit area, and then we are now talking that stress is a point wise description and the point does not have any dimension. Then the question comes, on the other hand, just now in the previous slides we see that we took a plane, and on this plane we show there are two component of stresses or 3 component of stresses, 1 normal, 2 shear stresses. Now, if the stress is a point wise description, then how can we have the shear stress, normal stress at a point, because point has no dimension, right? How can we have a plane at a point where the point does not have any dimension, right? Now, then what we do, there we introduce a term infinitesimal area and volume. What it means is, the point is not exactly a point, the point is idealized as an area or as volume. An infinitesimal volume, an infinitesimal area means it is a very, very small area, very, very small volume, which is in the limit sense actually a point. For instance, now if we have a point here, take a point like this, then around this point you take at a small area, small area if it is 2 dimension. Okay. Now, suppose this is dx, and this is dy, and then this area is dA, and dA is equal to dx dy, and dy is very small. Okay. Now, once we have idealized this, point as this infinitesimal area, then let us draw this area as this, represent this point as this, Now, remember, this is just I am showing, this is for the representation, this is as small as possible, this is infinitesimal, this term is very important. Okay. Now, once we have, this is the point here. Once we have this, then you see we have a plane here, 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 2 dimension. So, we can have stresses on this plane. And what are the stresses on this plane? Now, on this plane we can have a normal stress, just now we discussed a normal stress. On this plane we can have a normal stress, on this plane we can have a normal stress, again on this plane we can have a normal stress. All the 4 planes we can have normal stress. Similarly, we can have shear stress on all this plane as well. We can have shear stress on this plane, shear stress on this plane, we can have shear stress on this plane, we can have shear stress on this plane, and then we can have shear stress on this plane. Okay. If you are thinking that why these shear stresses are showing in this direction, here it is upward, here it is downward, then here this, you bear with us, we will discuss this, why they are, how this representation has to be made, and what are the sign convention and what are the coordinates, we will fix that in the next class. But here the point is, then we have one shear stress and one normal stress on each plane. How this normal stress and how this shear stress to be represented, what are the sign of this normal and shear stress, that we will discuss in the subsequent classes. Okay. Now, so this is called the entire thing, when you take this point, scoop out this thing here and represent this stress. So, if this point is P, let us, or any point, if this point is, say, if this point is x, then this is the stress at x. Representation of stress at x. So, how many components of stresses we have? We have on each plane, we have one normal component and one shear component. Okay. Total how many components? We will see that, okay, in the next class. Now, similarly, if we take a 3-dimensional object, which is subjected to this kind of load, and then we take a point. Now, around this point we consider a volume and then take the volume like this. Okay. And this is essentially, then it will be dx, it will be dy, and it will be dz. Okay. And this volume is very small, the infinitesimal volume. And then we have normal stress, this is normal stress. Since now it is 3D plane, so we can have just, you go back to the previous example, when we have a load on 3D direction, then we have 2 components, then we have one normal stress and the 2 shear stress, these are all shear stress. This is shear stress. So, everywhere, all these planes, all these 6 planes, we can have normal stresses and we can have shear stresses. Okay. Now, so what we have discussed today is that stress material characterization, or rather the understanding the material behavior when it is subjected to some kind of load or threat, it is an important, because it is a very crucial step required while selecting a material for a certain purpose. Okay. Then we also discussed that when we talk about material characterization, there are 3 important aspects. One is stress, one is strain, and then how these 2 stress and strain are related to each other, which is called material constitution. And then we discuss stress and strain are essentially the response of the material, two different response of the material when they are subjected to load. Now, stress is something which cannot be visualized, unlike strain. Stress is an experience, like the human body experiences stress. It is the same way material experiences stress. But on the other hand, strain can be visualized, it can be perceived, it can be measured. Now, then we discuss that stress or strain is a point-wise description, and since it is a point-wise description, and then also the stress is equal to force per unit area. To be consistent with these two definitions, we introduce infinitesimal area and infinitesimal volume concept, and then discuss how, if we take an infinitesimal area, then how the stress at a point can be represented, what are the different components of stresses in 2 dimension and in 3 dimension. We will stop here today, but before that, next class what we do is, next class we will start with fixing our sign convention of stresses, fixing our coordinate axis, and then see just here while representing these stresses in a graphical form, I showed shear stress in different directions, normal stress in different directions, why they are shown like this. Will we discuss that as well in the next class. Okay, then, so next class what we do is, next class we will discuss more on stress and of course strain, and then we will see different way, how the different way the stress and strain can be representative, particularly in a form of tensor. Okay, thank you, see you next class.